Good afternoon. The last few lectures we have been talking about sequential circuits. The basic building block of a sequential circuit is a flip-flop, but even those flip-flops are made of gates. We saw how a flip-flop is constructed. We saw several types of flip-flops, and then we used the flip-flop in some of the simple circuits. Counters is one. We talked about up counter, down counter, decade counter, ripple counter, synchronous counter, many different types of counters. We also talked about registers, shift registers, and some of the uses of shift registers. And we introduced what is known as a state machine, finite state machine, a circuit which has several states and it goes from state to state based on input considerations. Simple example is a traffic controller. You have red light, green light, yellow light. How long should you have a green light? How long should we have yellow light? How long should you have red light? And when it is done, what is the input trigger which makes those transitions possible? Simple example of a finite state machine. Even a counter is a finite state machine. You take a counter from 0 to 9, decade counter. It goes from 0 to 1, 1 to 2, 2 to 3, 3 to 4, etc. up to 9, comes back to 0, because it stays in each state for some time and then goes around. So, it is a finite state machine. We talked about non-sequential counters, counter which does not count in sequence, and then also it is a state machine because we have to say what is the state, present state, what is the next state, and so forth. Then we introduce inputs to these state machines. For example, up down counter is an example. There are, let us again take a decade counter 0 to 9. You may want to go from 0 to 9 at the input when a particular input is given, and go from 9 back to 0, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0 for another input, or the same input. In one state it is 0, the other state it is 1. So, these are all some of the examples we saw. So, in general, a generalized model or a block diagram for a sequential circuit is this: generalized model or generalized block diagram. Of a finite state machine. FSM stands for finite machine. You have a combination logic. Which has inputs called X, maybe n inputs. This is a purely combination logic. It has outputs, say m outputs. This is, we will say x1, x2, xn, z or y, z1, z2, zm, m outputs. As it is, this is not a sequential circuit. It is a combination of, this could be anything, gate level, multiplexers, whatever different decoders. But when we want the next state of this circuit, has to be decided based on the present inputs and the present output. So, you have to feed this back. This feedback is the one which makes it sequential, because these are nothing but flip flops, and a bunch of flip flops we said this a register. They are all clocked at the same time. So, whatever is the present state, that information is passed on after the next clock pulse to this input of the combination logic. So, combination logic decides the next states based on these present inputs and the previous output, then it becomes the next state for this. And this delay, flip flop delays the thing, because we do not want this to go on all the time, because it will be a racing condition, we do not want that. So, what is the speed at which you want to work can be decided by the clock that you go. Each of them is a flip flop, D flip flop, all clock at the same time. I am showing only one clock, but all of them, all these flip flops have this clock. So, this is a generalized model. Whatever you have seen till now, up counter, down counter, non-sequential circuit counter, everything falls in this. We have only flip flops, no external inputs, no external outputs. These are only states. We also saw a circuit in which same circuit can go from one sequence, go in one sequence for one x is equal to one value, 0 value, and go in another sequence, x is equal to 1 value. That is what we call up down counter. There we call the input x. So, we had 0 0 0 to 0 0 0 0 to 1 0 0 1, that is 0 to 9. When x is equal to 0, x is an external input. When x is equal to 0, then it goes from 0 to 1, 1 to 2, 2 to 3, etc. When x is equal to 1, it goes from 9 to 8 to 7, 6, 5, 4, 3, 2, 1. All that we have seen. Nothing new, I am just recap, sort of it's a recap of whatever I have been doing. So, let us try some simple sequential circuit today with inputs. See how to draw, how to, supposing a, see the counter is very simple, because the states were corresponding to the number we had to go through. Suppose I have a simple state machine. Why is it called machine? Do not worry about too much about the word machine. It is a state, goes from state to state, finite because the number of states is finite, machine is because those days everything was called a machine, that is all. So, it is a finite state circuit if you want to call it. So, supposing there are two states, S0 and S1. Circuit goes from S0 to S1 if x is 1, echo over there, x is 0, okay, and goes from S1 to S0 if x is 1. I am sorry, x is 1, x is an input. If x is 0, it stays here. If x is 0, so what is this circuit? This is a simple circuit with one input x and two states. This is a combination logic again. It has two states. If the present state is S0 and if you give x is equal to 0, it remains in x0, S0. If the present state is S1 and if you give x is equal to 0, it will remain in S1. If when you are in S1 you give x is 1 the input, it goes to S1 state. Similarly in S1 state if you give input x is equal to 1 it goes to S0 state. It is toggles between S0 and S1 if x is 1. It is a simple circuit. We have already seen all the types of flip-flops, characteristic equations, flip-flop, all that we have seen from this you can know it is nothing but a T flip-flop. We will see that, we will derive it now. Now, we will also assume there is an input, output. So, this is x, this output z, let us say p of them, p1, p2, etc. or 0, 1, 1, 2, 3 up to p variables. Now, how do you draw this circuit for this? Now, S0, S1 has no binary values. We have to make everything binary. How many binary variables do you need? There is only one state. I mean, there are only two states, S0 and S1. If you assume one variable, let us say A, if I can make A is equal to 0 for this, S1, and A is equal to 1 for, S0. This is called a state variable. This is state graph. These are S0, S1, etc. states. A is a state variable, it is a state table, this is a block diagram. Now, I have to draw, how am I going to get the circuit? I need corner map. Always finally the result is corner map. So, I will convert this into using zeros and ones. S0 is 0, so I will rewrite this. When you rewrite this, is called excitation table. The state table becomes excitation table if we give values for all the states. So, the present state A is equal to 0, present state 0, input x 0, input x 1, output z. Then 0, if you are in state S0 and input is 0, you remain in state 0. If x is 1, you go to 1. S1, A is 1, x equal to 0, remain in 1, x is equal to 0, you remain in 1, x equal to 1, you go to 0. And in S0 state, the output is 0, in S1 state, the output is 1. This is required for me to implement the logic, because this cannot tell me anything about the logic that is required. This will give me the logic required. So, how do you do that? All I need is a simple corner map. A and x are the inputs in corner map, then the next state A plus. I always told you, present state is marked A and the next state is marked A plus. Just to tell you, it is the state to which the circuit goes. There is nothing like A plus or A minus and all that here. Present state is A, next state is A plus, tells you that when you give us input, the circuit is taken to another state, variable will take a new value called A plus. So, if A is 0 or 1, x is 0 or 1. A is 0, x is 0, this is 0. A is 0, x is 1, this is 1. A is 1, x is 0. So, this is my A plus equation, and you know that we already talked about the different types of flip flop in the characteristic equations. In D flip flop, next state is same as the present input D is same as the next state. When T flip flop, we know what it is. For all the 4 flip flops, we know the characteristic equations. So, if I use D flip flop, this is same as D. Now, this is what? A bar x plus Ax bar is nothing but A exclusive R x. So, if I have this circuit, D, Q, there is only one flip flop required, only 2 values, state variable A is only one variable, it can only take 2 values. So, I will draw this like this. Now, this is x, which is A plus, this is A bar. So, this is A, this is x. Now, how does this A comes here? This A comes here from here, this is same as this. So, there is only one single flip flop. The output of this flip flop is fed back here, that is why it is called a sequential circuit, which is a feedback. So, there is only one flip flop. So, here if you look at the generalized diagram, this is the flip flop here, only one flip flop because there is only 2 states, and this is the combination logic. The combination logic's purpose is to drive the flip flop to the next state based on the previous state and the inputs. Based on the present state and the inputs, the flip flop is taken to the next state. So, next state, present state, next state becomes present state after 1 clock cycle. So, this is a simple circuit. Suppose I want to use a T flip flop here instead of D. Oh, I have to show the clock. Clock is important. T clock Q A bar. So, how does it work? If you give x here to the T input, x is 0, A remains same. If x is 0, the state does not change. If x is 1, the state changes to the next state. So, we know that in a T flip flop, T is 0, Q plus is Q. T is 1, Q plus is Q bar, previous Q. So, that is what we want. When x is 0, this is T I put as x. When x is 0, T is 0, that means the flip flop cannot work even though you give a clock. The output will remain whatever it was. If A is 0, it will remain 0. If A is 1, it will remain 1. On the other hand, when you make x is equal to 1, the T is equal to 1, it takes you from 0 to 1 or 1 to 0. That means it flips. Q plus is the complement of the previous Q. That is what it is. I can also do JK flip flop. We have seen all of them in the previous classes. See, we have been developing this sequence circuit starting from flip flops, how a flip flop is constructed, From there we draw the characteristic table, function table. We call it functional. Now we don't call them truth table because they don't simply start with 0 and 1, they have also the previous state not permitted, etc., etc. So we have the function table and we do the block diagrams, we do excitation tables and we use it to design up counters, down counters. We also talked about ripple counters, which is not used, these are all synchronous counters. Up counter, down counter without any inputs, it goes state to state, down counter goes from state to state. We can go for the full, suppose it is a 3-bit, you can go from 0 to 7 and back, or you can stop anywhere and go back to 0, all that we have seen. Then we talked about registers, and we also talked about non-sequential circuits, counters. Then we talked about registers, what is the use of registers, shift registers, there are 4 different types of shift registers, their uses, everything we have seen. We also talked about state machine the other day and we gave input X. Now this is the generalized treatment of state machine design, generalized block diagram. Now I will take one more example. This is a simple state graph is considered, only 2 states and 1 input variable and 1 output variable. We talked about a simple sequential circuit with only 2 states, 1 input and 1 output, and we could do it with 1 flip-flop. It could be D or T or JK. I didn't draw JK, but you can do it yourself. I will give you one more state graph and let us see how to design that. How to get a circuit out of that. Suppose I have a 4-state machine. These are 4 states called S0, S1, S2, S3. If you draw a line underneath and write the value, it becomes the output. Within the circle, if you write the value, a value 0 or 1, it becomes the output. So in this case, S0 has 0 output, this has 1 output, this is 0 output, 1 output. So this circuit is also simple circuit. This has 2 flip-flops, 1 input X, 1 output C, and this has 4 states. So there is a combination logic. So there will be 2 flip-flops. It can be D, T, anything. I am just make it D for simplicity of drawing. The present state, present input with present state together determine the next state. And the results are stored here in D flip-flops for it to become next state. So present state and next state will happen after some time depending on the clock frequency, depending on the clock time. So clock time, until the clock time expires, this has to be held here. So the D flip-flop will take the next value, store it, when the next clock comes, that passes it on to this. So this will be present state, input, one output and present next state here. This next state cannot become present state immediately because we cannot do it very fast, then we do not have any idea what is happening. We want to have it after the clock is arriving, next clock. That is why it is held here, and when the clock comes, this is transmitted to this after the clock. After next clock. Now, what are the transitions? Before I can design the circuit, I basically what I need to design the combinational logic. The design means design only combinational logic because flip-flops are already there. We know the output of this has to go into this and then next flip-flop, I mean next state and all that. So, what is the transition? So, since there is only one input x can take 0 value or 1 value. If x is 0, what happens? X is 1, what happens? From each state. So, x is 0 goes from S0 to S3. X is 1 goes here. X is 0 goes here. X is 1 goes here. X is 0 if x is 0, it remains in this state. I am sorry, x is 1, it remains in this state. X is 0, it goes back to this state. In this state, x is 0, goes here. We have to make sure that since there is only one variable, from each state there should be 2 arrows going out. One corresponds to x is 0, other corresponds to x is 1. This is important. We have to check this after drawing the state graph. So, this is the block diagram. This is the state graph. Next is state table. Before that, what I will do is, I will make there are only 2 flip-flops are required because there are 4 states. Number of flip-flops required is logarithm to base 2 of number of states. 4 states, 2 flip-flops. So, we will call these flip-flops A and B. The state variables, these are called state variables. There are 2 state variables A and B. That means S0 is 0, 0. S1 is 0, 1. S2 is 1, 0. S3 is 1, 1. So, instead of drawing in terms of S and then converting into 0, 0, 0, 1, etc., I will straight away write the state table. As I said, if you have only state variables, if you have only states S0, S1, S2, S3, such a table is called a state table. If you replace S0 and S1, etc., by the values of A, B or the flip-flop variables, such a table is called excitation table. The same thing. First you draw a state table. From S0 it goes to S3 or S1. From S1 it goes to S0 or S2. From S2 it goes to S1 or remains S2. S3 it goes to S2 or S1. if you draw like that and with outputs, then it is called as state table. Then instead of S0, S1, S2, if I use these variables values, same table is called excitation table. Anyway, I need this for flip-flop design. For drawing the corner maps, I cannot do corner maps with S0, S1, S2, S3, I need corner maps with A and B. So I will straight away write it to avoid one step. So I will call it excitation table, which is a next state of a next step of state table. I hope you understand this because there is no point in doing it again and again. So present state variables x value, next state variable, output. This is input, this is output. This is AB, I will call it input here, X, this is A plus B plus, output is Z. Now, 0, 0, X is 0, what happens? 0, 0, X1, what happens? This is S0 state, S1 state. If you draw lines like that, it is easy to write my A plus B plus and do the corner maps. So if present state is A 0, 0, X input is 0, what is the next state? You can see it from here. Present state is 0, 0, X input is 1, what is the next state? Z is output which is within the state, so whenever the circuit is in S0, output is 0. Whenever circuit is S1, the output is 1. Whenever circuit is S2, the output is 0. Whenever the circuit is S1, its output is 0. So this is easy to draw. Now, all I have to do is to fill in this A plus B plus. S0, 0, it goes to 1, 1. S0, 1, it goes to 0, 1. S1 to 0, S1, 0, it goes to 0, 0. S1, 1, it goes to 1, 0. S2, 0, goes to 1, 0, 0, 1. S2, 1, it remains there. S3, 0, goes to 1, 0. S3, 1, it goes to 0, 1. So I have neatly written the excitation table. Instead, I should have written S0, S1, S2, S3, X is equal to 0, it is going to be S3, S1. For S1, it will be S0, S2, S2 it will be S1, S2, S3 it will be S2, S1. All that instead of writing, I was straight away gone to this table, which is very easy to follow. Now, I need to find out what is inside this, because we already know there are T flip-flops whose this output is present state variable, these are the state variables, present state variables and next state variables. That is all I need. So there is two flip-flops which takes care of it. What I don't know is what is here, so that X along with the next state variables becomes Z and the present state variable. So the present state becomes next state or next state becomes present state is a sort of a chicken and egg problem. The chicken comes first and egg comes later, or the egg comes first and chicken comes later. That doesn't matter. If you call this present state, this becomes next state. If you call the present state, this becomes next state. There is no difference. Now, so I don't have to do anything except to design this combination logic block, which will give me output A plus, B plus and C. So I need to draw three maps, A plus map, A, B, X, A plus map, B plus map, Z map or C map. Fill in these values from this table here and then you got this design. Because we know that A plus is same as D plus, dA, B plus same as dB, I call this dA and dB. This is A flip flop, this is B flip flop, so this should be called a dA, this will be called dB. So I need dA value, dB value, so that the flip flop will be properly connected. So you draw A plus here, 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 0, 1, 0, 1, 1, 0. Is it right? 0, 0, 0 it is 1, 0, 0, 1 it is 0, 0, 1, 0, 0, 1, 0 it is 0, 0, 1, 1 is 1, 1, 0, 0 is 0, 1, 0, 1 is 1, 1, 1, 0 is 0, 1, 1, 1 is 1. 0, 1, 0, 1, 0, 1. Wait a minute. 1, 0, 0, 1. 0, 1, 0, 1. 1, 1, 0 is 1. 1, 1, 1 is 0. Am I making a mistake here? 0, 0, 0. First is 0, 0, first circle, first cell, second cell is 0, 0, 1. Third cell is 0, 1, 0. Fourth cell is 0, 1, 1. 0, 1, 1. Second circle, leave this 1. 0, 0 is 0. 0, 1 is 1. 1, 0 is 0. 1, 1 is 1, 0 is 1. 1, 1 is 0. Correct. B plus 1, 1, 0, 0. 1, 0, 1 1 0 0 1 1 1 is 0. This for B. Now, how do you draw this circuit? I have to have these two form A bar, B bar, X bar, A, B bar X, A bar Bx, A bar Bx bar.
Pritesh?
A bar Bx bar. Now, if you take out Bx bar, A bar from this and this, A bar times B bar X bar plus Bx, and you take X from these two will be A, B,
इसको बोला हाथ हिला
A
ही
bar
कर
Bx, A, B bar X, A Bx bar. So again you take A here, B bar X, Bx bar. So this is exclusive R, B exclusive R X. This is B exclusive R X. So again A bar. So you can also make this as Bx bar with the whole thing can be complemented and becomes A. That's what it is. Here it is easy. This one will be A bar Bx bar, A bar B bar, B bar X bar, ABX. This will be 0 0 1 1, 0 0 1 1, which is B. You can verify this. See, you know how to simplify Karnaugh maps. Maybe I might have in a hurry written something wrong. Don't jump on me on that. You know, by now you have seen enough of Karnaugh maps to go through it one more time. Don't just take my notes. Go through it and see if it's all right. Or I can use JK flip-flop, it's easier. If I use JK flip-flop, it becomes easier. So, what is the circuit now? I have two flip-flops, DA, DB, both are clocked same time. This is A bar. So D a combination logic I have already written. We have everything. We want A, B, C, I mean A, B and X. All are available, X is input. Here you have A bar, B bar because all of them are available, A bar, B bar, B bar, X bar. X has to be available both as two variable and an implement. So this is X, this is X bar. So you want to use X, you take it from here. You want X bar, you take it from here. So this is the circuit we want to design. I want to do three things in this. Because I have been doing everything myself and no response. I don't know whether you are following, whether you are really attempting, you are reading up. No idea for me. I just talk to screen and go back. So I want to do three things. One is first of all verify these equations. This is right. I am sure about it. Mapping usually when you do the same thing and then looking at this, notebook is one below the other. You can see here and do it. In a blackboard you see from here to here, laterally. Occasionally we make mistakes in mapping it, occasionally. And after that also we can make occasionally mistakes from grouping. So this is the grouping, this is equation and this is simplification. Similarly for B. So first of all, as I said, three things I want to do. One is verify the equations for dA, dB, dC. Exercise. Verify if it is a mistake, if there is a minor mistake somewhere, you can correct it yourself. If you are confident of how to do corner maps. Corner maps we have been talking from about third or fourth lecture. Today it is about, I don't know, 21st lecture I think. So many times, especially each lecture is 1.5 hours. So much corner map I have done in the class. So in fact I should not do all these things. I should have stopped here and asked you to do this yourself. I just want to go take you to the whole design process. That is why from next time onwards I am not going to do the corner maps. Then second, repeat the problem using D flip-flop, I mean T flip-flop. You know the characteristic equation for T flip-flop. And repeat the problem using JK flip-flop. All of them will have the same thing here. Up to this is the design consideration. Actually this is the design. This is mundane work. After doing the design, how are you going to implement using D flip-flop, JK flip-flop, Q flip-flop, I mean D flip-flop, JK flip-flop, T flip-flop. You have to draw corresponding corner maps and simplify the equations. And all the variables are available here. You don't have to go and generate these variables. Because I have used A, B, C, A, B, X, A bar, B bar is available, X may be, X bar may not be available, X is input, you may have to generate X bar. That is all you need to do, one inverter extra. Very simple. But if you keep on watching and then taking notes, you may not understand the whole thing. Only when you try problems. In fact, I have given assignments also. 3 assignments are already given, 4th and 5th I am working on. So assignments are given classwork, either you should follow the classwork, do this manner of some of this. When I do not complete it, you should try to complete this. There is nothing very big. I am not using equations or derivations or theory. It is a regular thing. Actually, I have done using JK flow here. I did not copy it here. I derived JK D flip flop, but in my notes I have worked out JK flip flop for this. You can also do that. If you want JK flip flop, my equations are JA, KA, is only answers I will write. J and K are same, Bx bar. JB X bar or A bar. KB. Verify this again. Again it may be wrong. I mean not deliberately wrong, no conceptually wrong. Maybe some slip in copying from one table to another, maybe some slip in grouping, maybe some slip in writing this grouping. So this also I have given you. Z is same always. B. Output is B. All these circuits which you have seen so far, circuits with input and output, earlier in counters we did not see outputs. In counters there are states. In a regular counter, up or down there is no input, only states, goes from state 0 to 1, 1 to 2, 2 to 3, etc. Coming back to 7 to 8 and then go back, start again. On the reverse, start from 7, 6, 5, go back to 0. No inputs. Okay? Then in up down counter we had our input. When x is 0, we have to count up. When x is 1, we have to count down. So again same as counter state diagram with x is equal to 0 or 1. This is the one for which today what I have done is a generalized model where I said there are outputs also possible. States, inputs and outputs, and we draw the state graph accordingly. States, inputs, outputs is within the states. For that only you do this. These circuits, state graphs with inputs of course, output given for a state. In this case S0 has 0 output, S1 is 1 output, S2 is 0 output, S3 is 1 output. The output is defined for a given state. Such a circuit is called a Moore circuit. This one. Moore circuit is a circuit in which output is defined for a given state. Output is defined for a state. Example, in this case, S0, S2, 0 output, S1, S3, 1 output. There is another type of circuit called Mealy circuit. In a Mealy circuit, the output is not defined within the state, it depends on the arrows. For a present state, if the present input is this, the output is this. For this present state, if the input is this is the output. So, output is defined for a given state and a given input. That means, instead of drawing 0, 1, 0, 1, if I get x is equal to 1, the output is this much. X is equal to 0, the output is this much. If I do that, this becomes a Mealy circuit. Now, we will take one example of Mealy circuit and do the design. In practice, you find more Mealy circuits than Moore circuits, and Mealy circuit requires a little less hardware, not a whole lot less, somewhat less compared to Moore. Compared to Moore, Mealy has a little less hardware and also used very often. Example of a Mealy circuit. Again, we will have a state diagram with 4 states. We did not write the outputs within the circle, so we can write these states within the circle. Output is written outside based on the inputs. Again, these are 4 variables, 4 states, 2 state variables. 4 states require number of state variables is number of states logarithm to power 2 of number of states. Logarithm to 4 is 2. So, 2 state variables. We will call it A and B again. Now, the state graph itself is going to be like this. Now, input is x, output is z or z. So, when you write this in the arrow, you first write x and then z. So, if you have 1, 0, if the circuit is in S0, if the input is 1, the output is 0. That is what it means. The arrow means When the circuit is in S0, if the input is 1, output is 0. In S0, if the circuit is input is 0, the output is 0. If in the circuit S0, if the circuit is in state S0, if you give input A0, it goes to S1 and produces output 0. One, 0. Input is 1, output is 0. Input is 0, output is 1. This is the circuit 1, 1. From S2, if the input is S0, the output is 1, circuit goes to S3. If in S3 the input is 1, it goes to S1, output is 1. From S3 it goes to S0, the input is 0, the output is 0. This is a Mealy circuit, this is a Moore circuit. Moore circuit, states define the outputs. This state is 0 output, this state is 1 output, this state is 0. In Mealy circuit, the state and the input decide the output. See, in each of these states, the circuit can be in more than one clock cycle. Circuit can remain in S0 for several clock cycles because X is whatever. Then it can go to 1. Supposing X is 1, it goes to S1, but then you keep this. It will be here, for example here. Circuit is in S2, input is 1, it remains in S2. It doesn't say one clock cycle, it can have several clock cycles. Here also it is the same thing. Circuit can be S0, in S0, and the input is 1, output is 0, it will continue here as long as the circuit is in S1 state. So now what do? We do the state table. Percent state. Table, what is a state table? State table is where you use SS. Of course, X will be given, Y, Z will be given, but you will say S0, S1, S2, S3. In excitation table, instead of S0, you will put AB, 0, 0, S1 instead of S1, you will put 0, 1, etc. So, we will use that. You are in 0, 0 state, X is 0, it goes to S1 state, and the output is 0. If you are in circuit AB, input is 1, it remains in S0, producing the output 0. This is S0. S1, 0, 1. In S, if X is 0, it goes to S0, it produces an output of 1. If it is in S1 and the input is 1, it goes to 1, 0, whereas the output is 0. S2, in S2 the input is 0, it goes to S3, output is 1. So it is S2, the input is 1, It remains in S2 giving an output of 1. S3 is detected as in S3, the input is 0, it goes to 0 0, output 0. If in S3 the input is 1, it goes to 0 1, produce an output of 1. Now I can draw corner maps for A plus, B plus, Z. I can use D flip-flop, design the circuit by drawing corner maps for D flip-flop, T flip-flop, JK flip-flop. You have to do this yourself. I have told you how to do that. So to summarize, all that we have done in sequential circuits, we have done 15, 16, 17, 18, 19, 20, 21. 7 lectures on sequential circuits, each 1.5 hours. Lot of time, 10.5 hours of sequential circuits. We started with the definition of sequential circuit with the feedback and memory, the basic building block, flip-flop, how the flip-flop is, first how do you do the latch using gates, how does the latch become flip-flop. We saw SR flip-flop, D flip-flop, JK flip-flop, T flip-flop, with and without with clocks, with after that we wrote the excitation table. First of all, we wrote the function tables, how the flip-flops work. Then we do the excitation tables. Excitation table tells you what input needs to be given for a flip-flop to go from 0 to 0, 0 to 1, 1 to 0, 1 to 1. And then using the flip-flops, we design counters, first ripple counters, where the output of the previous flip-flop goes to the clock as a second flip-flop. The sequence, the ripple counter is a problem of delay because it has to go to ripple as the clock has to ripple through. We still saw up counter, down counter, binary counter, 4 bit, 3 bits. We also saw decade counter, how to count up to 9 and go back. We also saw how to start from 9 and go to 0 and go back to 9. We also saw arbitrary, we can stop in anywhere. Suppose I count from 0 to 11 is possible. And then we looked at sequential circuits, synchronous counters, where the delay of the clock is not there. The only delay of the flip-flop is the delay of the propagation time of the hardware within the flip-flop, which is not very much, insignificant. That way we can run synchronous circuits, synchronous counters for much higher frequencies compared to ripple counters. After designing synchronous counters, we also showed you how to design a synchronous counter, 3 bits, 2 bits, 4 bits, up or down. Then we went to registers Yeah, we also saw what are known as arbitrary sequence counters, not counting in sequence, counting in any fashion, both in ripple counter as well as synchronous counter. We saw that. And then we went to registers. What is a register? Register is a set of flip-flops, inputs and outputs. You can load the input to new values. The output remains the same as long as you don't change the inputs. So you need a clock. All these flip-flops have reset and clear. You can reset it to 0. I mean 0, clear to 0, reset to any given value, 1. And then we talked about different types of registers and their uses. We talked about shift registers, going the output from one flip-flop to the next input, and you can do it, it will go out, or you can recirculate it to keep the content constant. We also saw the use of shift register, serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out. Each one we saw the serial in, serial out, for example, gives you a delay. Serial in, parallel out gives a conversion of serial signal to parallel, serial bit stream to parallel. Parallel to serial gives the conversion of parallel bit stream into serial bits. Parallel in, parallel out uses memory. And then we also saw some other applications of shift register, pseudo-random signal generator. Then we defined state machines. What is a state machine? State machine is nothing but a circuit with different states. Any sequence circuit has a state. A counter has a 3-bit counter has 8 states. Only thing, it goes from state to state automatically without any inputs. As long as the clock runs, it goes. In a state machine, same thing, the concept is states. Machine is because it is a word which has been used from previous mechanical thing, but don't have to worry about machine. Finite state machine means it has a finite number of states. Again, even the counters can be designed using finite state machines. So we saw finite state machines, simple. We saw the generalized block diagram. We saw a simple circuit with 2 states with 2 states will require 1 flip-flop. Then we saw a circuit with 4 states which requires 2 flip-flops. So basically consists of a combinational logic and flip-flops. The combinational logic is designed for taking the present state and the previous output to come up with the next state. These are called flip-flop driving circuit. You drive the flip-flop input using the combinational logic, which takes into account the input at this present time and the output of the past, and then comes with the new output. And then we saw some examples. And all of this can be designed using D flip-flop, T flip-flop. Combinational logic is simple, gates. But flip-flops can be J, K, D, J, K, D, T. We saw all that. And then we talked about Moore machine and Mealy machine. Moore circuit means the output is remaining within the state. Each state an output is defined. The Mealy machine output is defined for a state and an input. If a circuit is in particular state S0 and the input X is 0, what is the output? Input X is 1, what is the output? Such a machine is called a Mealy machine. We also saw an example. We drew for all of them state graph. First of all, the block diagrams, state graphs, state table which uses SS, S0, S1, S2. Then convert them into state variables. How many state variables are required depends on how many flip-flops and how many flips are required depends on the number of states. Up to 4 states, 2 flip-flops, up to 8 states, 3 flip-flops and so forth. And once you have this, you draw the excitation table. That will give you the inputs to the corner maps. You draw the corner maps, find out the inputs for each flip-flop, And that is the combination logic we are talking about, and then we can do it. Any circuit in digital can be designed using this. I already started today with the lecture, and I started the lecture today with the example of a state traffic controller, lift controller, everything. What are the state? There are, let us say there are 8-story building, 0 floor to 1, floor 1 to floor 8. Which floor it is? Is the input is going up or going down? If the input is 0, it will go up, let us say. Input is 1, it goes down. Suppose the circuit is in, the lift is in state 5, floor 5. If we give an input of down, and then you shall have to say when. Within the lift, you go and give 3. So instead of 5, it will go to 4 and then to 3 and stop. So these are all state machines. Most of the digital systems we use in practice, day-to-day practice, are sequential circuits, and they are all synchronous because high speed is required. So with this I stop today, and then we'll. So far we have only used, given a state graph, how to define, how to interpret the state graph, and how to design combination logic and the flip-flop inputs. The complementary problem is, suppose I give you a problem, how do you draw the state graph? From a word statement. Again, take the lift example, you say this building has 8 floors and we have these inputs and I want flashing lights. All that I give you, and then you have to draw the state graph. Once you have a state graph, again this design is same. So drawing a state graph from the problem statement is the important step. That is the most important step in a design. You have to understand the problem, draw the state graph. Once you have the state graph, you know all the tools. State graph to state table, number of flip-flops can be chosen, number of states, this has number of flip-flops. From there you know the excitation table, from there you know the flip-flop equations, from there you know the circuit. So how to draw state graph for a given problem statement, we will see in the next lecture. There is no class on Wednesday. This Wednesday I am not taking the class. So we will meet again next Monday, which is the 8th of April. I will stop here now unless you have a question. Is there any question? Go ahead.
Sir, sequential circuit, more than one state is sequential circuit. One state is only in, that is called combinational circuit. That's true?
You have to. I don't understand you. Talk again clearly.
Only one state is there in a finite state machine, that is called combinational circuit. More than one state is there, then it is called
Why do you have to always simplify whatever I say? Who says that? One state alone is one flip-flop. I don't know whether it is a combination circuit or a sequential circuit. It's up to you to decide. A state graph has more than one state.
More than one state.
One flip-flop has one
that
flip-flop
I have
has.
read, so I have confused it.
The first problem I took today was 2 states. Is it not? S0, S0, S1. And when S0 goes to S1, if X is equal to 0, or X is 0, it remains in S0, otherwise it goes to 1. Similarly, in the S1 state, if it remains X is equal to 0, then otherwise it comes there. It's a single flip-flop. More than one state. There is nothing like a one state machine. I don't know, if you want to call it that, you call it. I have no problem.
One state machine is combinational circuit. On books told.
Sir, I don't want to take your definition. This is unnecessarily confusing. Why do you have to do this every time? You have to simplify it. Not necessary. Nobody is going to ask you a question whether a one state machine is a combination logic. It is just trick questions not required. I am teaching straightforward. Okay?
Okay. Another one. Sequential circuit means present input and past output is the sequential circuit. That is told.
The next state depends on the present state and the present output. Okay.
Present. Okay. In the common sense, they told sequential circuit is behavior pattern. Pattern of behavior that is in a event manner. That is told in there. That is true. We want a behavior pattern as per sequence of event.
I will teach next week about this. I told you. I am going to give you how to start with a pattern and how to design the circuit. Okay?
Pattern of behavior means every state is one pattern of behavior.
Why don't you wait for next class? Next class I am going to talk about pattern generator. How do you, given a pattern, how do you identify it? We will do it.
Okay, okay, okay.
Sir, your problem is, Mr. Dinesh, your problem is you read so many books and then come to me. As I have requested you, please do not ask questions like this because other people will get totally confused. You come to me in the beginning of the class 10 minutes early, you ask all your questions, I will answer you.
Can I close, sir?
Yes.